Okay, problem 67. We are given a circuit with two capacitors in parallel, a switch, and a resistor. Now notice that there's no EMF, there's no battery here. So automatically that tells me that I'm going to be looking at a different formula for a discharging capacitor. So once the switch is closed, and that looks like Q max e to the negative t over tau, right? I don't know exactly when we're going to need this yet, but I'm just saying it's important to notice that this is probably what we're going to be using, because we have an RC circuit with no EMF, and switch closes, this equivalent capacitance is going to discharge. So what are we asked to find? We are asked to find how much charge remains on the 3 microfarad capacitor after 1 millisecond. Okay. So this was fully charged. These were fully charged by a 12-volt battery. So we had a battery, but it was disconnected. Okay. So the first thing we need to do, let's find Q max. So Q max is equal to delta V times equivalent capacitance. Now, notice that our capacitors are in parallel, so that means that we can just sum them up straight, because capacitors are summed opposite of the way that resistors are summed. So we have a 5 microfarad capacitor equivalent capacitance. Okay, we also had a 12-volt battery. This was the maximum charge, right? This was what we were before the switch is closed, before we start discharging. These are charged by a 12-volt battery, and the equivalent capacitance is 5 microfarads. So that gives us 60 microcoulombs. Okay, tau, our time constant, is going to be R times C, which gives us 500 ohms times 5 microfarads, which gives us 2.5 milliseconds. Okay, good. We're doing great. So we found tau, we found Q max. Now, so the system is going to discharge after the switch is closed. After switch closes. Let's write this fast, because I'm sure that's really exciting to watch me write stuff down. Okay, so using our formula, we have everything we need. So now we were told that we want to know what it is after when t is equal to 1 millisecond. So let's just plug everything in. Q is equal to Q max, which is 60 microcoulombs. Right? E to the negative, it's going to be 1 times 10 to the negative 3, was it millisecond? Seconds over 2.5 times 10 to the negative 3 seconds. So those cancel, those units cancel. Now we're left with 60 microcoulombs times e to the negative 0.4. That's going to give us a value of 40.23 microcoulombs. Okay, so notice that we started out with 60 microcoulombs on the system. This system had 60 microcoulombs of charge. After 1 millisecond, we're down to 40.23 microcoulombs of charge. So that's what's left over. So now we want what's left over of the change in the potential for the equivalent capacitance. Okay, that's going to help us determine what we need to know. So what do we have here? We have Q max, I'm sorry, this is Q leftover. This is what we just found. Q leftovers over C equivalent, that's going to be 40.23 microcoulombs over 5 microfarads, and that's going to be 8.04 volts. So we were at 12, now we're at 8.04. And now we can, and this is 8.04 volts on the equivalent capacitance here. So now we can actually find what we were looking for, which is the current, or sorry, how much charge was remaining. Okay, and we can do that. Let's see, 3 on the 3 microfarad capacitor. We can do that by this. We'll call this Q3 is equal to 8.04. This is the leftover potential difference. Remember, it's QVC, right? Q is equal to the change in potential times the capacitance. So now we have 3 microfarads. That leaves us with 24.12 microcoulombs. That's how much charge is left on this capacitor. We can also find it on the other one for fun. I'm not sure if we're even asked to do this, but we have all the tools to do it right here. Why not just go and do it? You also, we could do it this way, or we could also do it another way. We could also do it by just taking what we had initially minus this. So what was it? It was for leftover Q earlier we had, it was 40.23 microcoulombs, and then we can take it, subtract this one, 24.12, and then we're still left with about the same answer. Either way, Q2 is approximately 16.1 microcoulombs. Oh, we were asked to do that. Good. And we just did it without being prompted. How about that? Okay. Next, we need to find the current in the resistor. So the equivalent resistance is in parallel with the resistor, and we're going to be able to just use Ohm's law here. Okay, so this we're going to take, we want the current is equal to the change in potential over the resistance. The change in potential of the system that we just found out that was left over after the time that it was closed, 8.04 volts over 500 ohms. This gives you a value of 0.01608 amps, or we could call that 16.08 milliamps, or 16.1 milliamps.